Thank you all for being here today to attend my dissertation defense. I really appreciate it. So today I'm going to talk about the quantification of community resilience against wind hazards. And I'll start off by talking a little bit about what drove me to pursue this research topic and what are the motivations behind it. And I will begin and I'll begin with some stats about the destructive impact of windstorms like hurricanes and tornadoes, which will be the focus of my dissertation. So in the period between 1950 and 2011, on average, tornadoes kill about 92 persons per year, and the hurricanes kill about 51 persons per year. In terms of losses, around 40% of the total losses between 1997 and 2016 are related to tornadoes, while 38% are related to hurricanes and tropical storms. And as we can see here in these photos from the tornado outbreak at Moore or the damage from Hurricane Michael, most of these fatalities and the losses are related to the collapse and the damage of the built environment during these winter storms. So having a more resilient built environment can really reduce these fatalities and the loss significantly. To provide more understanding of the big picture here, let's take a look at this figure. It shows that the risk of a disaster happening from wind hazard is a product of three main components. The hazard component, a hurricane or tornado needs to happen in the first place for a disaster to occur. The exposure component, which is where does this storm hit? For example, when hurricanes are moving over the Atlantic Ocean, no one gets hurt, so no disasters could happen. So there should be a living community exposed to the hurricane or the tornado for a disaster to happen. And finally, the resilience component, which is how much is the exposed community resilient to this wind storm. If a tornado hits a very resilient community, no damage will occur, which means no disaster will happen. So as we can see here, the level of resilience of the exposed community is an important factor as it will determine if a disaster will occur or not. And this will bring us to an important question here, which is, are we confident about how resilient the exposed communities are? Is Miami ready for the next hurricane? Is Joplin prepared to take another tornado? Or in other words, how can we measure their resilience level to be more confident about their future? To answer this question, we first need to define resilience, which is, according to the National Academy of Science, community resilience is the ability to prepare and plan for, absorb, recover from, and more successfully adapt to actual or potential adverse events. And to measure or quantify the community resilience, we will need a vulnerability model that will use the community pre-hazard conditions and the potential hazards as an input to calculate the amount of immediate damage and losses, which will be used by a recovery model to estimate the community recovery trajectory, then the community resilience. So there are two required models to estimate the community resilience, which are the vulnerability model and a recovery model. And this will bring us to the outline of today's presentation. Today, I will talk about the vulnerability and recovery modeling of residential communities that are subject to hurricane winds. Then I will present a framework to model the impact of hurricane rainfall. And finally, I will cover modeling of wind-borne debris in tornadoes, as wind-borne debris is one of the major sources of damage in tornadoes. So let's get started with the vulnerability of residential communities subject to hurricane winds. What is the physics of the problem? We have a subdivision of residential buildings that is subject to a hurricane. Once the wind pressure on the building envelope exceeds its resistance, the building envelope components will get damaged and potentially becomes airborne. The wind-borne components would potentially hit buildings on the downwind side and cause more damage. This breach in the building envelope will induce internal pressurization that could lead to more damage and more wind-borne debris. So we have two damage mechanisms here: excessive wind pressure and the impact of wind-borne debris. The two mechanisms are progressive. The damage keeps progressing gradually as the hurricane approaches the community. They are interdependent and cascading. Once the first damage occurs, more damage will occur as in the domino effect. And due to this cascading and interdependency nature of the damage, the neighboring subdivisions can also have a destructive impact on our considered subdivision, what we will call here as the effect of exogenous wind-borne debris. By taking a look at the literature, we will find that the effect of exogenous wind-borne debris has not been studied yet. So what I'll be presenting today is a time-stepping approach that models the full track of the hurricane while modeling the debris flight using a 6 degree of freedom trajectory model and also account for the exogenous wind-borne debris. And I'll start off with the exogenous wind-borne debris. This figure shows a plan of buildings with an arbitrary configuration. The considered subset of buildings, or what we refer to as the considered subdivision, is in the dark gray area and enclosed in this solid black line, which is represented by gamma CS. The light gray area is the neighboring subdivisions that needs to be modeled to account for the exogenous wind-borne debris, which is represented by gamma NS. So mathematically, gamma NS can be written as gamma CS plus some sort of an enlargement function, which is alpha here. And our target is to find the proper alpha that will capture all possible exogenous wind-borne debris while minimizing the total area of the neighboring subdivision. And this can be written as the following optimization problem. By looking at this problem, we can realize that excuse me, defining a generic alpha exo that can fit any arbitrary boundary is computationally intractable, as for each boundary shape, there will be a different alpha exo. The way I will handle this problem is by reformulating it for a single building case, and this will be helpful for two main reasons. The first one is the boundary of the neighboring buildings can be assumed to be circular in the single building case, and the circles are more manageable to deal with. And the second one is the single building case can be easily generalized to a neighborhood with any arbitrary boundary by simply taking the union of all buildings required area. And this can be formalized as follows. We first need to find the omega for a single building case, then generalize the solution by taking the union of all omegas. By looking at the new optimization problem here, we will find that we need to estimate NXO, which is the number of exogenous wind-borne debris hitting the building. And the question here will be, how will we estimate this number? To answer this question, we need to know the source of exogenous wind-borne debris, which is the damaged components of the neighboring buildings, and the driving force of the debris flight, which is the hurricane wind velocity. So we have neighborhood-related factors as well as hurricane-related factors, and all of them are associated with uncertainties. There are uncertainties in the building strength, uncertainties in the hurricane track, heading, pressure drop, wind speed, etc. These uncertainties will be handled using the Monte Carlo simulation method, and the problem statement will change to maximize the expected NX. So in summary, the simulation strategy will increase the radius incrementally using a predefined delta R. Then measure the number of exogenous wind-borne debris for each size step. Once the expected NXO max out, the RXO will equal to this size step. And the damage estimation model used in this simulation is an engineering-based vulnerability model, which estimates building damage due to excessive dynamic wind pressure and debris impact. Okay, let's take a quick look at some details on how exactly I calculate the wind pressure and debris loading. The debris linear and angular velocities used to estimate the debris impact energy are calculated using a three-dimensional 6 degree of freedom debris trajectory model. As we can see here, wind-borne debris objects are in red and the houses are in blue. The internal pressure coefficients are estimated using Holm's internal pressure model, and the external pressure coefficients are obtained from the wind tunnel database provided by Tokyo Polytechnic University. Both damage mechanisms are a function of the hurricane wind field, which is estimated by adding the environmental scale component and the storm scale components algebraically. The environmental scale component is estimated based on the hurricane eye translational velocity, and the storm scale component is estimated by solving the momentum equation of the slab boundary layer. Let's move on to the application part. So the presented methodology is applied to a gable roof archetype, and the 10 construction cases are considered here. A building strength factor is defined for each construction case as the weighted average of the all components resistance, which is described by this equation. And based on this figure, construction case 1 is the weakest, and construction case 10 is the strongest. The layout is chosen with 3 different floor area ratios, which is basically the ratio between the area of the buildings in the plan to the total ground area. A floor area ratio of 0.6 represents a densely populated area, and 0.1 represents a sparsely populated area. In this study, we explored the effect of Vmax, which is the hurricane maximum wind speed, and the floor area ratio, and the building strength factor on the required RXO. And we need to note here that all the RXO results reported in this study are normalized with using the Rmax, which is the maximum flight distance for the debris. We can see here that as the maximum hurricane wind speed increases, the required RXO increase. This is due to the increase in the number of debris flying in the wind field. In the second figure, we can see that as the studied area becomes more densely populated with buildings, smaller extents of neighboring subdivisions become sufficient to capture all the exogenous wind-borne debris. And at the last figure down here shows that in general, building strength does not influence the required RXO except for very weak construction cases. They require significantly smaller RXO as compared to moderate and strong construction cases. The main reason for that is weak construction cases tend to get damaged at very low wind speeds, and these low wind speeds are not sufficient enough to carry the dislodged components far enough to impact the considered building. As a result, the required RXO are lower here. We concluded this study with a regression analysis to summarize all the results into a mathematical expression that can be used directly in the future without the need to rerun the simulations. 3 main regions are used in this analysis. The first one at Vmax below 55 meters per second, RXO equal to 0. The second region is defined by this purple expression, which corresponds to the weak construction cases. And the last region is defined by the dark area expression, which corresponds to the moderate to strong construction cases. We can observe that big portion of the simulated domain shows a value of RXO that is actually bigger than the Rmax itself, which emphasize more on the cascading and interdependency nature of the damage from wind-borne debris. So we concluded the first study, and we will move forward to the second one, which is risk and fragility assessment of residential wooden buildings under hurricane winds. The performance of residential wooden buildings under hurricane winds is typically described qualitatively using a hierarchy criteria. The descriptive format of this criteria is stated as no damage, minor damage, moderate damage, severe damage, and destruction. These qualitative measures are quantified using damage states, which are governed by the performance of the building envelope as shown in this table. To quantify the building performance probabilistically based on these damage states, fragility functions are required, which reads as the probability of the building damage states exceeds a certain damage state given a specific hazard intensity, which is the maximum 3-second gust wind speed experienced by the building during the hurricane passage. The hurricane-imposed risks on the residential wooden buildings can be now defined as the annual probability of failure which is obtained by convoluting the building fragility function with the probability density function of the annual maximum hurricane wind speed as shown in this integral. So the fragility function is a key here, and it is required to both quantify the performance of the building probabilistically and estimate the hurricane-imposed risks. Deriving an analytical solution for this function is intractable, so it is evaluated here in this study through a numerical scheme. And this numerical scheme is based on the Monte Carlo method, and it is summarized in this flowchart. For each hazard intensity level, a three-dimensional geometric model of the building and the surrounding buildings within a distance of Rxo is generated virtually to account for the damage from wind-borne debris. Then a hurricane is sampled such that Vmax equal to the specified hazard intensity, and the building's resistance is sampled from the relevant distributions afterward. Finally, the building damage state is estimated using the engineering-based vulnerability model, which is described earlier. At the end, the estimated discrete values of the fragility functions are used to fit a log-normal distribution. Here, we applied this methodology to a gable roof archetype. Analysis cases are 10 construction cases, 3 floor area ratios, and 11 Vmax. For the results of this study, I'll be more focused on showing the significance of including wind-borne debris damage on the estimated fragilities, as this is the main contribution here. Fragilities due to wind pressure damage have been around for a while, so I'll focus more on the effect of wind-borne debris. Okay, in this figure, the solid lines represent the fragility curves, not including damage from wind-borne debris, and the dashed line includes the damage from wind-borne debris. We can observe that in general, the damage from wind-borne debris increases as the floor-to-area ratio increases. Here I am showing the ratio between the probability of failure in the debris case over the no debris case, and there are 3 main observations. The first one, all paths that crosses this red zone are cases where the probability of failure increased due to the inclusion of wind-borne debris in the damage analysis. The second observation is that generally the increase in the probability of failure varies between 0 to 310%, which emphasizes on the importance of including the damage from wind-borne debris. Last one is we can clearly observe that the damage from wind-borne debris increases as the floor area ratio increases, which we also observed in the fragility curves. And this will conclude this study. Now, we covered the vulnerability and the damage estimation part, and we will move on to the recovery and resilience part. So we mentioned earlier the definition of the community resilience. Here, we will work more on formulating it mathematically so that we can quantify it. As shown in this figure, community resilience, referred to as R, is estimated by normalizing the integral of the community recovery function Q with respect to the recovery time TR. Estimating the community recovery function hinges on the hazard intensity, the community vulnerability, as well as the recovery process, all of which are uncertain. And to account for these uncertainties, we need to quantify the community resilience probabilistically by estimating the cumulative distribution function of R. We will find that deriving an analytical solution for this function is intractable, so a stochastic simulation approach is proposed here in this work, which is the basis of the presented framework. So to wrap up, our goal is to quantify the community resilience measure R probabilistically by estimating its cumulative distribution function using a stochastic simulation approach. The stochastic simulation approach uses the Monte Carlo simulation algorithm for the estimation of the CDF of R. We can find the flowchart of the proposed framework on the left side of the slide here. And for each realization, R is estimated using the community resilience measure integral. And the community recovery Q is estimated by aggregating building recovery functions. The building recovery function is estimated using a new building recovery model, which is based on three functionality states: not safe in red, safe with some services off in yellow, and safe with full services in green. By services here, I mean things like electricity, water, internet, gas, etc. Okay, we know that the work progress for the recovery activities typically advances continuously over time, while the functionality state it changes only at the completion of a group of activities. For this reason, the level of functionality associated with the functionality states is modeled using the Heaviside step function, and it is either 0 or 1. 0 means residents evacuate or didn't return back to the building after the hurricane event, while 1 means they returned back or didn't evacuate in the first place. In particular, the level of functionality, as we can see here in the graph here, of the NS state is 0 and the SFS state is 1. And for the SSO state, the one in yellow here, it is either 1 or 0, since the building is safe to occupy, but there are some services off. In this functionality state, the residents may choose to return back to their residence or not. A decision like that hinges on the level of the damage of the building itself and its surrounding buildings and the socioeconomic status of the residents. In this building recovery model, this is considered using the probability of functionality loss given the SSO functionality state. Okay, so this is the idea of the building recovery model. Now the question is, how will this conceptual idea be able to model the recovery of each building in the community? The answer is using a newly defined resilience limit states that are introduced here in the building recovery model to translate the damage sustained by each building to a corresponding recovery function. In particular, 5 resilience limit states are defined here, which are named as minimal damage, minor occupiable damage, moderate unoccupiable damage, severe irreparable damage, and complete collapse. Each one of these resilience limit states has a unique combination of the following recovery activities: inspection, evaluation and planning, repair activities, and demolition and replacement. Okay, so to conclude, there is building damage and the building recovery functions that consists of 3 functionality states. What exactly is the recovery path of the building? This will be specified by the resilience limit state this building is in. Keeping in mind that these resilience limit states do not just deal with each building as a separate entity from the surrounding community, they actually factor the condition of the building surroundings in the recovery path calculation, and this is described in more details in this paper. Finally, the damage sustained by each building is estimated using the engineering-based vulnerability models that we mentioned earlier. Now let's go to the application part. This framework is applied to a residential neighborhood in Miami, Florida, to quantify its resilience to hurricanes probabilistically. The neighborhood consists of 513 buildings. Surrounding buildings are also modeled to account for the exogenous windborne debris. The community population is modeled using available census data about Miami-Dade County. In particular, the number of residents per building follows this probability mass function. Hurricane generation is controlled by the single-site probabilistic hurricane hazard model, which subjects the neighborhood to 15,000 hurricanes with a category that follows this distribution. In this video, we will see some part of the simulations. A single family, gable roof archetype is used to model the buildings. We can see the windborne debris here highlighted in red, flying in the hurricanes, wind field, impacting other buildings and causing more damage. To show the capabilities of the framework in differentiating various construction cases and the mitigation strategies, 2 construction cases are considered: the as-built case and the enhanced case, which applies enhancement to the wind pressure and debris impact capacities as a suggested mitigation plan. We can see that the presented framework is able to capture the improvement in the performance of the enhanced case over the as-built case, which is reflected in the expected community recovery function conditioned on the hurricane category. And this will lead us to conclude the results with the goal of this work, which is the cumulative distribution function of the resilience measure conditioned on hurricane category. Again, the improvement in the performance of the enhanced case over the as-built case is captured by this right shift of the CDFs of R. Okay, we talked about the vulnerability and recovery modeling for hurricane winds. Let's move on to the impact of hurricane rainfall. Hurricanes are typically produce severe and widespread rainfall, and this rainfall causes significant damage to the built environment and its supporting infrastructure. In particular, the damage caused by rainfall to the buildings happens progressively over two stages. In the first stage, rainwater seeps into the building under the influence of the wind, what we call wind-driven rain, through the perforations in the building envelope, leading to potential damage in the internal content, and in some extreme cases, it can damage the structural system itself. The second stage happens when the rainfall persists over a longer period of time. This could saturate the ground and overwhelm the surrounding drainage system, leading to inland flood. So, a fundamental step here to accurately estimate the damage caused by hurricane rainfall to residential communities is to quantify the amount of water ingress occurring during both stages, wind-driven rain and inland flood. And let's take a look here at this integral on the left side. What we basically need to estimate the amount of water ingress due to wind-driven rain is the wind-driven rain intensity over the building envelope and the perforation area in the building envelope. The perforation areas or the damaged areas can be calculated using an engineering-based vulnerability model. Either these perforations are caused by a hit from wind-borne debris or by the wind pressure. Both are considered in this model. For the wind-driven rain intensity, we will estimate that using an Hilarion multiphase model, which I will describe in more details shortly. The estimate of water ingress due to the inland flooding stage requires the estimation of the flood inundation depth at each building. To do so, we need a coupled hydrodynamic model, which I will also provide more details shortly. So let's start with the wind-driven rain intensity. Two main steps are required here. In the first step, the time averaged wind speed is estimated around the buildings by solving the Reynolds average Navier-Stokes equation with the realizable K epsilon turbulence model. In the second stage, the Eulerian multiphase model uses the simulated wind speed to model the wind-driven rain field. And more details about this model can be found in this paper by Zicheng Ouyang and Professor Spence. For the inland flooding, the TRIPS model uses the community layout, land use, topography, vegetation, soil characteristics, and the meteorological data like temperature, humidity, radiation, horizontal rainfall, etc., to model the relevant hydrologic processes such as evapotranspiration, infiltration, rainfall interception, etc. The output is the temporal variation of the surface runoff, referred to as capital R here, which is then used by the OFM model to propagate the surface runoff in the residential communities using the shallow water equations. More detailed about this coupled hydrodynamic model can be found in this paper by Kim et al., and the model itself is provided by Dr. Donghu and Professor Valeri. This framework is applied to Houston, Texas to simulate Hurricane Harvey rainfall. On the right-hand side here, we can find the full track of Harvey, and on the left-hand side, we will find the simulated part of the track. as at the very beginning and the very end, Houston was not affected by Harvey. A neighborhood that consists of 580 buildings is modeled, and three construction cases are considered, which are named as weak, moderate, and strong construction cases. Here is the simulated Harvey on the right-hand side of the slide, and on the left part is the simulated wind speed versus the data obtained from NOAA. So Harvey impacted Houston as a tropical storm. So the wind speeds are amplified such that it impacted Houston as a category 2 and 3 hurricanes, just to study more what if scenarios, as this will help us in understanding the role of each of the wind-driven rain and the inland flooding. And I will conclude the results of this study by this figure. This black line represents the average flooding depth at all buildings in the considered community, and the green one represents the average water depth inside buildings due to wind-driven rain for the original Harvey winds, which was a tropical storm. The yellow lines are when Harvey is amplified to a category 2, and the red lines are when it is amplified to a category 3. We can see here as the hurricane intensity increases, the water ingress from wind-driven rain becomes more significant. It can even exceed the flooding in some cases. This shows the importance of considering both wind-driven rain and inland flooding while planning to mitigate the consequences of hurricane rainfall, as both require really diverse mitigation actions. For example, while mitigation measures like dams, levees, flood walls, etc., can be efficient in mitigating the damage from flooding, these measures do not mitigate damage from wind-driven rain. So accounting for both is really important to provide a more comprehensive picture of what could happen. And this concludes the hurricane rainfall part. And now I will move on modeling wind-borne debris. Excuse me, I just take a sip of water. And now I'll move on to modeling wind-borne debris in tornadoes. How can we quantify damage from wind-borne debris? Four main components needs to be identified. Nature of debris objects. So based on damage surveys, the damage components of buildings constitutes the majority of the debris objects in the windstorm, and they can be categorized based on their shape as compact objects, plate-like objects, and rod-like objects. Number two is number of debris objects in the wind field, which can be initially determined using a pressure damage model. Number three and four, the debris landing location and its impact energy upon landing, which requires a debris trajectory model. And this trajectory model is what I'll be presenting in this section. I'll start off with the modeling approaches. We have 6 degree of freedom models and 3 degree of freedom model. The 6 degree of freedom model is actually good to estimate the trajectory of all shapes of debris, while the 3 degree of freedom model is considered a good approximation for the compact debris only. Both of them require tornado wind field model to calculate the aerodynamic forces and moments. The tornado wind field model simplifies the tornado wind field velocities into 4 main components: translational, radial, circumferential, and the vertical velocities. Okay, let's take a quick look on a previous research work here. We will find that previous research work in tornadoes was mainly based on the 3 degree of freedom trajectory model. And what I'll be doing here is to develop a solution strategy for the 6 degree of freedom model in a tornado wind field. The solution strategy uses the debris initial conditions, tornado parameters, and wind tunnel data as an input to solve the equation of motion using a predictor-corrector time marching scheme, which continues to update the parameters, defining the wind-borne debris trajectory for each time step until the debris object falls on the ground. A very high-level illustration of the predictor-corrector scheme is the The predictor time marching step starts from the current value of the parameter of interest, then calculates an initial guess for the next time step via the Euler method. The corrector time marching step improves this initial guess using the trapezoidal rule to obtain the value at the next time step. We applied this model to predict the trajectory of a 4x8 roof sheathing that is shown on the right-hand side here. The roof sheathing is subject to 3 tornadoes, small, medium, and large, and the position of the tornado track with respect to the initial location of the sheathing is shown here at the bottom right. Convergence analysis is carried out, and we can see that the numerical algorithm is conversion here. So I will conclude this study by 2 videos. The first one to show the difference between straight line wind field and tornado wind field. The trajectory of the straight winds is in red, and the one in blue is for the tornado. As we can see here in this video, the straight line wind produce a very different trajectory than what the tornado will produce, which emphasize on the need of this kind of models for tornado debris. As we can see that straight line winds is actually approximation is actually not accurate enough to capture this curvature that happen in tornadoes. The second video. Okay. The second video, and here is to show why 6 degree of freedom models. And here in this video, I will show trajectory of 3 roof sheathing that have the same exact initial conditions, except that they have different initial yaw angle, or in other words, they are generated from buildings with different orientation. As we can see here, the black trajectory has 0 yaw angle, and the red one has positive yaw angle, has negative yaw angle, sorry, and the blue one has a positive yaw angle. Why this will show the importance of the 6 degree of freedom model? Because the 3 degree of freedom model does not have theta2 as an input parameter. So the 3 degree of freedom model will not feel these variations, and all of them will have the same trajectory. While as we can see in this video, each one of them has very distinct trajectory. And this will conclude the tornado debris study. Before closing, I would like to highlight the key contributions, which are an engineering-based hurricane vulnerability model is developed here that can account for exogenous wind-borne debris and also used to develop fragility functions for the combined action of wind pressure and debris impact. Community resilience is also quantified probabilistically, and to do so, new building level recovery model is introduced, as well as resilience limit states. Modeling hurricane rainfall is carried out comprehensively by accounting for both wind-driven rain and inland flooding. And finally, a wind-borne debris trajectory model for tornadoes is developed. This trajectory model is 6 degree of freedom and uses a tornado wind field. At the end, I would like to thank my advisors, of course, Professor Seymour and Professor Jason, for all the support and the guidance they gave to me during my PhD. I would also like to thank my dissertation committee members, Professor Sharif and Professor Seth. I'd like to thank all my collaborators in this work, Professor Valeri, Zicheng, Donghu, Andrew, Lab 1267 team, both Spence and Jeffers sides, my family and friends, and the whole CEE community. And of course, we don't want to forget our sponsors. So big shout out to the NSF and the Raqam International Student Fellowship. Thank you.
Okay, so thank you very much, Ahmed, for that very nice presentation. At this point, what I would like to do is invite everyone who has a question to go ahead and ask that question. This is the part of the dissertation defense that is open to the public. So if anyone in the audience has a question, please feel free to go ahead and ask Ahmed.
Seymour, this is John. I'll ask a question if that's okay.
Yeah, sure.
Oh, okay, great. Well, so yeah, fantastic work, impressive. I was curious, and maybe you touched on this, but you know, for a lot of the modeling, of course, you're using principles of physics, but when it comes to like a system level validation, you know, when we do these large models, we're often asked, and of course, you can do field studies and things like that. But what steps did you take to do some level of validation, you know, at component and system and larger level, if you did?
So there are there are many components here. For example, in the engineering-based hurricane vulnerability model, it consists of a pressure damage model that has been validated before, and I am using it. It consists of a debris trajectory model that has been also validated before, and I am using it. On the system level, when like connecting all of them and validating all these models with data from the real world, I haven't touched this part yet. But on the level of each single model, each one of them are physics based and has been validated on their own. Even for also the modeling for hurricane rainfall, also these like the inland flooding one has been validated for the case study of Houston itself, and for the wind driven rain, this model also has been validated. So yeah, on the single model level, these models has been validated, but on the whole system level, it hasn't been validated yet.
Okay, thank you.